So when we talk about an atom losing electrons or gaining electrons in order to get an octet, how is it that we're figuring it out other than looking at the electron configuration? There's another way for us to help us figure this out. And in the last chapter, we talked about an idea called ionization energy, the ability for an atom to lose electrons, the ease of it, and the atomic size, how big it is. And if you take these two ideas and you kind of smash them into a new idea, incorporating both, you get a new idea. That this new idea is what's called electronegativity. And so if you remember when we talked about ionization energy, we said that some atoms, the ionization energy, it's just going to be too hard to remove an electron. Why would it be so hard to lose an electron? How's that going to affect it? Well, if it's going to be hard to lose an electron, maybe it's because it doesn't want to lose them. Maybe it wants to gain electrons, right? And if it's so big, if an atom is really big, how hard is it going to be for it to lose electrons? Well, maybe it loses them really easy because it's so large. So a new idea was kind of smashed together to describe both of these things in one pocket. And so that idea is what's called electronegativity. And electronegativity is defined as the ability of an atom to attract another atom's electrons. So if you have two atoms next to each other and they have their structure, their electron configuration with the electrons and the orbitals that they have, how easy is it for one to take the other one's electron? It's a measure of that. And so by definition, electronegativity is the ability of an atom in a chemical bond to attract another atom's electrons. Now, when we say, how do we tell? Well, there's a number scale for it. The number scale ranges from 0 to 4. What does 0 mean? What does 4 mean? What's in between 0 and 4 mean? Well, when an atom has electronegativity that's near 0, or 0, even better, that means that the atom has 0 desire, 0 attraction for another atom's electrons. It must mean that it doesn't need them because it's stable. If you have an atom that has electronegativity of 4, that means that it really wants an electron from another atom because obviously it's not stable. And so by gaining an electron, it becomes stable. And then between 0 and 4 means everything sort of in between, right? So this table here is you can have it as a list, but I think an easier way of looking at it is a table, as sort of a version of the periodic table that shows you the electronegativities. And what it allows us to do is look at all the atoms together and say, all right, what are the atoms that really are attracted to electrons and want electrons to become stable, which ones don't? So you notice that the lowest of the low, you have cesium. It's got the lowest desire for electrons on this chart. And then all the way on the top right, you have fluorine with 4. So what this means is that cesium has a very, very, very small desire for electrons in order to help it become stable. Whereas fluorine has a very high desire for electrons in order for it to become stable, and then there's everything in between, okay? So when you look at this whole chart, of course, you've got to figure out, why that is. Why is electronegativity this way? Well, it boils down to how big the atom is and how easy of a job it can do whatever it's going to do to become stable. So if you think of these atoms like cesium is really big and doesn't do a great job of holding onto its electrons. So its ionization energy must be really low and the size must be really big. So it can't even hold onto its own electrons, let alone attract another one. Fluorine, on the complete opposite end of the spectrum here, is a really small atom and it doesn't have a lot of shielding electrons. And so it can really hold onto its electrons really well. Also, it ends in S2P5. So if it gains another electron by gaining another electron, it ends up in S2P6 and becomes stable, okay? And these guys all do the same thing by gaining an electron. However, since they're larger and larger and larger, they have a little bit harder time doing it. Whereas cesium, it would rather lose an electron to become stable because it's ending in S1. So yeah, it can gain, but man, it would rather lose electrons to become stable. And that's how you kind of interpret this as to if you have two atoms next to each other, who's going to gain, who's going to lose electrons.